with acids and bases. Arrhenius concepts of acids and bases. Arrhenius, a Swedish chemist, was the first to define acids and bases in an aqueous solutions. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which, when dissolved in water, give hydronium ions or hydrogen ions. Accordingly, all mineral acids like HCl, HNO3, and H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ions. HCl in water gives H plus Cl negative ions. HNO3 in water gives H plus NO3 negative ions. Arrhenius names these acids which dissociate completely in water as strong acids. There are other acids like acetic acid and carbonic acid and phosphoric acid which when dissolved in water do not dissociate completely into ions. As a result, an equilibrium is set up between the ions and the undissociated water molecule as shown below. Like in acetic acid, in H2CO3, H3PO4, there is an equilibrium within their respective ions. Arrhenians name these acids as weak acids. According to Arrhenius, a base is a substance which contains hydroxyl group and which when dissolved in water gives hydroxyl ions. The substances like sodium hydroxide and potassium hydroxide, which when dissolved in water dissociate completely to give hydroxyl ions. Therefore, NaOH in water gives Na plus OH negative ions, KOH in water gives K plus and OH negative ions. Arrhenius named these bases which dissociate completely in water as strong bases. There are substances which do not completely dissociate into hydroxide ion. Arrhenius named these substances as weak bases. For example, substances like ammonium hydroxide, magnesium hydroxide, and aluminum hydroxide do not dissociate completely to give hydroxyl ions and can be written as you can see, there is an equilibrium which is established between their molecule and their respective ion in ammonium hydroxide, in magnesium, and in aluminum hydroxide. Hydrogen ions obtained from the acids and hydroxyl ion obtained from the bases combine together to form unionized water. Arrhenius described this combination of H plus and OH negative ions as neutralization reaction. NaOH gives Na plus and OH negative ions. HCl gives H plus and Cl negative ions. Combining right sides of the equation, cancelling the common ions on both the sides, we get H plus OH negative gives H2O, that is neutralization. Arrhenius concept is very simple to apply and explains a number of phenomena like neutralization, hydrolysis of salts, strength of acids and bases. However, there are certain limitations which are described below. Arrhenius' concept of acids and bases is applicable only in aqueous solutions. This concept fails to explain the acid or base behavior of substances in non-aqueous mediums, such as liquid ammonia, liquid sulfur dioxide, alcohol. Secondly, Arrhenius' concept fails to explain the acidic character of substances like CO2, SO2, and SO3, and basic character of substances like ammonia, sodium carbonate, and calcium oxide. Arrhenius' concept also fails to explain the reaction between an acid and a base in the absence of water. For example, ammonia plus HCl gives ammonium chloride and Na2O plus SO3 give Na2SO4 solid. Although Arrhenius' concept of acid and base suffers from a number of serious limitations, yet the concept is very useful and informative for an elementary approach. Bronsted-Lowry concept. Arrhenius' concept of acids and bases was further improved by Bronsted and Lowry. Both Bronsted, a Danish chemist, and Lowry, an English chemist, in 1923 incidentally introduced the same definition for acids and bases. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton, whereas a base is a substance which can accept a proton. In other words, an acid is a proton donor, whereas a base is a proton acceptor. As a result, Lowry-Bronsted concept is sometimes called the proton donor acceptor concept. Acid 1 giving H plus base 1, base 2 plus H plus giving acid 2. According to Bronsted-Lowry, a neutralization reaction involves the release of the proton by an acid and the acceptance of that proton by a base. For example, the reaction between HCl and ammonia to form the salt ammonium chloride can be represented as you can see, ammonia plus HCl combining to form ammonium plus chloride ions. The curved arrow shows how electrons must rearrange to result in the transfer of hydrogen atom from the acid to base. The pair of electrons on the nitrogen of ammonia is attracted by the partial positive charge on the hydrogen on the polar hydrogen chloride molecule. A comparison of the structures of the reactants and the products shows that the hydrogen atom which was bonded to chlorine atom in the reactant is bonded to nitrogen in the product. Thus, a proton has been transferred from chlorine to nitrogen. To act as a Bronsted-Lowry base, a species must have at least one unshared pair of electrons so that it can form a covalent bond to the proton. To act as a Bronsted-Lowry acid, a species must contain at least one hydrogen that is attached to an atom that is more electronegative than hydrogen. In this case, HCl loses a proton and is an acid. Ammonia accepts a proton from HCl and it is a base. Some other examples of acid-base reactions according to Bronsted-Lowry concept are HCl plus H2O, H2SO4 and H2O, and H2SO4 plus ammonia. It is important to note in the above examples that water acts as a base with respect to hydrochloric acid and sulfuric acid. Interestingly, water acts as an acid with respect to ammonia. Such a substance which acts both as an acid proton donor as well as a base proton acceptor is called amphoteric or amphiprotic substance. Similarly, bicarbonate ion behave as an acid and a base, like bicarbonate ion combine with ammonia to give ammonium ion and carbonate ion. HCl plus bicarbonate combines to form H2CO3 and chloride ion. Other examples of amphoteric substances is hydrogen sulfate, conjugate acid-base pairs. Let us reinvestigate a reaction between an acid and a base. HCl plus ammonia gives ammonium plus chloride ion. HCl being an acid donates a proton from chloride ion, whereas ammonia being a base accepts a proton from ammonium ion. Now the chloride ion has a tendency to accept the proton, whereas ammonium ion has a tendency to donate a proton. In other words, an acid donates a proton and becomes a base, and a base donates a proton and becomes an acid. Thus, a base formed from an acid is regarded as the conjugate base of the acid. Similarly, the acid formed from the base is called conjugate acid of the base. In the examples above, between HCl and ammonia, chloride is the conjugate base of HCl and ammonium is the conjugate base of base ammonia. Acids and bases that are relatively related by the loss or gain of H plus are called conjugate acid-base pairs. Thus, chloride and HCl, ammonium and ammonia are conjugate acid-base pairs. We can represent the acid-base pairs as acid giving conjugate base plus H plus giving conjugate acid. It is clearly indicate that any acid-base reaction would involve two acids and two bases. These acids and bases are called conjugate pairs. For example, acid 1 plus base 2 gives acid 2 plus base 1. HCl plus water gives a conjugate acid plus conjugate base as hydronium ion and chloride ions respectively. In the above example, HCl is an acid since it donates a proton and chloride is its conjugate base. Water accepts the proton and hence is a base. Thus hydronium ion is the conjugate acid. A strong acid has a weak conjugate base and vice versa. Some other examples of conjugate acid bases are cited below. You can see. It is a further important to note the Bronsted-Lowry concept is not restricted to only neutral molecules. The concept is equally applicable to ions as well. A careful inspection of the above discussion reveals that a substance is capable of showing acidic character only if the other substance is capable of showing accepts a proton. That is the base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene doesn't accept H plus from HCl. Not only neutral solutions, not only neutral molecules, but cations and anions may act as acid or bases. Both Arrhenius and Bronsted-Lowry concepts require an acid to be a source of proton. Thus, all Arrhenius acids are Bronsted-Lowry acids. According to Arrhenius, a base is a substance which gives hydroxyl ions in the solution. That is sodium hydroxide giving Na plus NOH negative. Whereas according to Bronsted-Lowry, a base is a substance which can accept a proton. For example, this carbonate plus H plus giving bicarbonate. Carbonate cannot give H hydroxyl ion in aqueous solution. It is therefore cannot be an Arrhenius base. Thus, all Bronsted-Lowry bases are not Arrhenius bases. Limitations of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcomings of Arrhenius concept, yet it could be not answer some of the well-established reactions. For example, it cannot explain the reaction between acidic oxides like CO2, SO2, SO3 with the basic oxides like calcium oxide, barium oxide, and magnesium oxide, which takes place even in the absence of water. For example, calcium oxide plus SO3 giving calcium sulfate. Clearly, in the reaction between calcium oxide and sulfur trioxide, there is no proton transfer involved in the reaction. The acidic nature of compounds like BF3, FeCl3, and AlCl3. Least concept of acids and bases. Jean Lewis in 1923 proposed a more general definition of acids and bases, which is based upon the donation and acceptance of electron pair. According to this concept, an acid is a substance which accepts a pair of electrons. A base is a substance which can donate the pair of electrons. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbitals to accommodate one or more pairs of electron can act as a Lewis acid. On the other hand, a base is an electron pair accept donor. It means that any substance with unshared pair of electron can behave as a Lewis base. Thus, the acid-base or neutralization reaction involves the formation of a coordinate bond between the electron pair donor and the electron pair acceptor. For example, the reaction between boron trifluoride and ammonia is a typical Lewis acid-base reaction. Let us now discuss in detail Lewis acids. According to this concept, Lewis acids are classified as molecules having central atom with incomplete octet of electrons. Boron trichloride, boron trifluoride, aluminum trichloride are acids of this type. It is clear that the central boron and aluminum atoms have only 6 electrons. Simple cations. All the cations are short of electrons and can behave as Lewis acids. Large size cations like sodium, potassium, calcium, barium behave as weak Lewis acids. This is because these have little tendency to accept electrons. On the other hand, small size cations such as H plus, silver, and lithium ions have a strong tendency to accept the pair of electrons and are strong acids. In addition, highly charged cations have a higher tendency to accept electron pairs relative to lower charged cations of given metal. For example, stannic is a stronger Lewis acid than stannous. Some of the typical examples of Lewis acid base reactions are given below. Ag plus ammonia giving AgNH3 whole twice plus 2 plus 1. Copper plus 2 plus 4 chloride ion giving CuCl4 2 negative. Molecules in which central atom has weak available d orbitals and may acquire more than 8 electrons. Compounds such as AlCl3, SiF4, SnCl4, SbF5, and SO3 are Lewis acids, whereas the central metal atom can expand its valence shell, like AlCl3 plus chloride ion giving AlCl4 negative, and tin stannous tetrachloride, tin tetrachloride plus Cl negative gives SnCl2 6 negative, SnCl6 2 negative. Molecules with multiple bond between atoms of dissimilar electronegativities. Carbon dioxide represents an interesting example of a double bond between carbon and the more electronegative oxygen atom. Oxygen, being more electronegative, has a tendency to attract the shared pair of electron more towards it in CO2. As a result, it acquires positive charge on the carbon atom and becomes electron deficient Lewis acid and attaches with the oxygen of the hydroxyl ion. Similarly, sulfur trioxide acts as a Lewis acid towards water. Lewis bases. According to this concept, Lewis bases may be classified as one of the following types of substances. Negatively charged ionic species. All the negatively charged species are Lewis bases because they are rich of electrons and have a strong tendency to donate electron pairs. Common examples are chloride, oxide, hydroxide, amide. The greater the charge density of the anion, the stronger is the base. Third, neutral molecule with one or more unshared pair of electrons. Molecule with unshared pair of electrons acts as a Lewis basis. For example, ammonia, water, ether acts as electron donors. Alkenes and alkynes with multiple bonds also form coordination bond with metal ions in organometallic compound. Acid-base reactions according to Lewis concept. Some of the typical acid-base reactions involving the formation of a coordinate bond between a Lewis acid and a Lewis base are summarized. जैसे कि combination between H plus and ammonia you can see, combination between BF3 and F negative you can see to form tetrafluoroborate, and combination of calcium oxide and sulfur trioxide to give calcium sulfate. As you can see, it is important to note that an empty orbital is being created on the sulfur atom by moving a pair of electrons from the doubly bonded onto the oxygen atom. Again, combination of cupric ion with ammonia. And lastly, the combination of SnCl4, combination of stannic chloride with ethers to give an adduct. Lewis acid-base concept discussed above is widely used because of its simplicity in understanding many acid-base reactions. In spite of its wider applications than Arrhenius and Bronsted-Lowry concept, it has several disadvantages which are discussed below. Lewis concept is too general and considers all reactions forming a coordinate bond to be acid-base reactions. This is, however, not always true. According to Lewis concept, some of the transition metals that form compounds with CO carbon monoxide, such as nickel tetracarbonyl, iron pentacarbonyl, etc., are acid-base reactions, which is not correct. Formation of a coordinate bond between acid and a base is the basis of Lewis concept. However, the well-known acids like HCl, HNO3, H2SO4 don't form any coordinate bond with the bases such as potassium hydroxide or sodium hydroxide. Accordingly, HCl, HNO3 and H2SO4 should not be regarded as acids according to Lewis concept. Lewis concept doesn't give any uniform scale of acid and base strength. So these were the few limitations of this part. Now coming on to the Lux fluid concept of acids and bases. A new concept of acid and base was proposed by Lux in 1939. This concept was further extended by Fluid in 1947. According to Lux fluid concept, an acid is any substance which accepts an oxide ion, whereas a base is any substance which gives up oxide ion. Thus, Lux fluid acid bases can be represented as base is a calcium oxide giving calcium plus 2 plus oxide ion, lead oxide giving lead plus 2 and oxide ion, sodium oxide giving Na plus and oxide ion. Lux fluid acids can be represented as SiO2 giving Si4 plus oxide ion. Thus, Lux fluid acid base reactions can be represented as silicon dioxide silica plus calcium oxide giving calcium silicate. Similarly, CO2 plus barium oxide giving barium carbonate, SO3 plus lead oxide giving lead sulfate, and iron P2O5 phosphorus pentoxide plus Na2O giving sodium phosphate. According to Lux fluid concept, substances that show a tendency to lose as well as gain electrons gain oxide ion are termed as amphoteric. Zinc oxide represents an interesting example of amphoteric character. For example, zinc oxide can lose oxide to form zinc plus 2 ion in addition to zinc oxide gaining an oxide ion to form zincate ion, zinc oxide giving Zn plus 2 plus oxide ion. Similarly, Al2O3 can behave as an acid as well as a base in Lux fluid sense and hence can act as amphoteric, which is Al2O3 giving Al plus 3 and oxide ion basic. This concept of Lux fluid is very useful in high temperature, especially in glass ceramic industry and metallurgical operations. The concept of Lux fluid can be extended to halides and sulfides in place of oxygen. For example, AlF3 plus sodium fluoride giving Na3LF6, carbon disulfide plus sodium sulfide giving Na2SCS3. Again, Yusanovich concept of acids is a very general and takes into consideration all concepts of acid and bases proposed by Arrhenius, Lowry Bronsted, and Lewis acids. In addition, Yusanovich concept includes all oxidizing agents as acids and all reducing agents as bases. Thus, according to Yusanovich concept, an acid is a substance that reacts with a base, gives up cations, accepts electrons. Similarly, Yusanovich concept defines a base as a substance that reacts with an acid, giving up anions or combines with the cations. This is not much important as it is not prescribed in our syllabus. Yusanovich concept is very useful as it classifies all examples of acids and bases together. However, it is too general. This is because it considers even the oxidation, reduction, redox reactions as acid-base reactions. Now coming on to the next wider concept, that is solvent system concept. Solvent system concept of acids and bases was postulated by Caddy Islay in 1928. It is an extension to the Lowry-Bronsted concept, and it's applicable to both protonic as well as non-protonic solvents. According to this, an acid is a substance which either by direct dissociation or by interaction with the solvent gives a cationic characteristic of the solvent. A base is a substance which either by direct dissociation or by interaction with the solvent gives the anionic characteristic of the solvent. Characteristic cations and anions of the solvent are the ions producing during the autoionization. The prefix auto means self. To illustrate this concept, let us consider the autoionizations of some protonic acid, in which water plus water giving hydronium ion plus hydroxyl ion, acetic acid plus acetic acid giving acetic cation plus acetate anion, SO2 plus SO2 giving SO2 plus SO3 2 negative, N2O4 plus N2O4 giving NO plus and NO3 negative, H2SO4 and H2SO4 giving H3SO4 plus and HSO4 negative. For example, HCl behaves as an acid in water solvent as it gives the cationic characteristic of water, say hydronium ion. Similarly, ammonia acts as a base in water as it gives the anionic characteristic of water. It is important to note that acetic acid behaves as an acid in water as it produces the cationic characteristic of water. Acetic acid behaves as a base in sulfuric acid as it produces the anionic characteristic of the solvent sulfuric acid. Now, urea dissolves very readily in water and gives neutral solution. However, urea dissolves in liquid ammonia and behaves as an acid because it gives the cationic characteristic of the solvent ammonia. Similar to Arrhenius concept, neutralization reaction may be represented as the combination of cationic characteristic of the solvent with the anionic characteristic of the solvent to form the solvent molecule in non-aqueous medium. Some of the neutralization reactions in various solvents are given below. This in liquid ammonia in acetic acid plus SO2 plus N2O4. It is important to note that neutralization according to solvent system concept is the reverse of autoionization reactions. Now again coming on to the types of solvents. Solvents are classified in a number of ways on the basis of their physical and chemical properties. Broadly, there are three ways in which solvent can be classified: protonic and aprotic solvents. Solvents which contain hydrogen and can lose hydrogen in the form of a proton are called protonic solvents. Common examples of protonic solvents are water, ammonia, H2S, and HF. Solvents from which hydrogen cannot be obtained in the form of a proton are called aprotic. Common example acetonitrile and benzene. Solvents like N2O4, SO2, CCl4 are called aprotic solvents. Acidic, basic, and amphiprotic solvents. Solvents which have a strong tendency to give protons are called acidic solvents. Common acidic solvents are H2SO4, HF, acetic acid. Solvents which have a strong affinity for protons are called basic solvents. Basic solvents like ammonia, hydrazine, pyridine. Solvents which can display both acidic and basic properties are called amphiprotic solvents. Example of amphiprotic solvents are water, methyl alcohol. Third is ionizing and non-ionizing solvents. Solvents which undergo self or auto-ionization are called ionizing solvents. Typical examples of ionizing solvent are water, ammonia, hydrogen fluoride, sulfur dioxide. Solvents which do not ionize are called non-ionizing solvents. Typical examples of non-ionizing solvents are benzene, CS2, and carbon tetrachloride. Such solvents are non-polar and have low dielectric constant. Then, relative strength of acids. The strength of protonic acids can be compared easily by the tendency of acids to give protons. Protonic acids like HCl, H2SO4, HNO3 ionize completely to give protons, whereas acids like acetic acid, HF, and HCN ionize completely to give protons. Acids which ionize either completely or to a very large extent are named strong. On the other hand, acids which ionize to a smaller extent are named weak acids. These protonic acids, namely HCl, H2SO4, and HNO3, are weak, strong, whereas acetic acid, HF, and HCN are weak. It is the extent of ionization of an acid which measures the strength of acid. Let us consider the ionization of an acid, which may be represented as this. Equilibrium constant is written as this, where H plus A negative He are the concentration of undissociated acid, Ha, A negative salt, H plus ion. K is the known as the dissociation constant or ionization of the acid. Magnitude of K measures the relative strength of acid. The stronger is the acid, the larger is the value of Ka. It is convenient to use the term pKa to express the dissociation of an acid. Just pK is equal to minus log Ka is equal to 1 upon log Ka. A larger value of pK means that the acid is little dissociated. It implies that the acid is weak. As larger the value of pK, the weaker is the acid. Now you can refer to this table. You can refer to this table to find out some of the common pK values of the most common acids. A close inspection of table this reveals that the strong acids have negative pKa. Of all the acids given in the table 7.1, HBr is the strongest acid. Trends in acidic strength. We have learnt that the relative strength of acids in aqueous solution can be easily expressed in terms of pKa value. The higher the value of pKa, the weaker is the acid, and vice versa. pKa values of some binary hydrides are given in this table, table 7.2. Let us evaluate how the acidity of binary hydride depends upon the nature of compound, its molecular structure, its position in the periodic table. Comparison of pK values of binary hydrides reveal that on moving from left to right across a period, the strength of binary acid increases. Acid strength of binary acids along the second period decreases as HF, then H2, then ammonia, then CH4. The observed trend can be easily explained on the basis of electronegativity of element as one move from left to right across a period. It is very important to note that size doesn't change greatly across the period. With the increase in the electronegativity value of the central atom, the tendency to pull the electron pair from the hydrogen increases. This facilitates the release of hydrogen in the form of a proton and makes the hydride more acidic in the character. On similar considerations, we can explain how the acidic strength of binary hydrides of third period decreases. This HCl, then H2S, then pH3. Comparison of the pKa values Comparison of the pKa values of binary hydride reveals that the relative strength of acids increases as one moves down the group. An inspection of the pKa value reveals that hydrogen fluoride is a weaker acid than hydrogen iodide. Relative strength of halogen group 7a decreases as, similarly in group 6a, strength of acids increases as one move down the group. Water is a weaker acid than hydrogen telluride. Actual order of the acidic strength down the group in the periodic table cannot be explained solely on the basis of electronegativity considerations. For example, in group 7th, fluorine being the most highly electronegative element should pull the electrons pair towards itself in HF. As a result, the release of hydrogen in the form of proton should be highly facilitated, making HF the strongest acid. In fact, HF is the weakest acid. Anomaly can be explained if we take into consideration the size of central atom. As one moves down the group, the electronegativity decreases, but the size of atom increases as shown below. Effect of increase in size of the atom is more than the decrease in the electronegativity value of central atom. A proton can be more easily removed from a binary hydride in which the central atom is bigger in size as compared to an atom which has smaller size. Hi can release the proton more easily than HF. As a result, Hi is the stronger acid, whereas HF is the weakest acid among the halogen acids. The acidic strength of hydroacids can be easily explained with the help of Born-Fagen-Haber cycle, which takes into consideration of all the factors that determine the strength of acids in water. The acidic strength of an acid, let's say Hx is equal to FClBrI, can be represented by the equation Hx giving H plus X negative. Overall reaction can be thought to occur in various steps which are outlined and detailed below. You can refer to the above table. Hx is dehydrated to give HXX gas. The energy absorbed in this step is called the dehydration energy. Hx is dissociated into the constituent atoms, namely hydrogen and halogen. Energy absorbed in this step is called the dissociation. Ionization of the hydrogen atoms occurs to give H plus ions. Energy absorbed in this step is called ionization energy. The gaseous halogen atoms are converted into gaseous halide ions. The energy released in this step is called electron affinity. Gaseous hydrogen ions are hydrated to give H plus ions. The energy released in this step is called hydrational energy of hydrogen ions. The gaseous halogen ions are hydrated to give X negative ion. The energy released in this step is called hydrational energy of halogen ions. Strength of the acid or the heat of ionization is given by the summation of all the energy steps involved and may be given by the expression delta H dehydration plus T plus ionization energy plus electron affinity plus hydration plus hydration. In the expression 7.1, EA and E delta HH plus hydration, delta HX negative hydration are negative because energy is released in these steps. The energy values in kg per mole of different steps of various halogen acids are given in table 7.3. You can refer to this table to find out. On the basis of energy released during the overall process, the strength of the acid can be represented in the order HI, then HBr, then HCl, then HF. Strength of organic acids. Organic acids possess either a carboxylic acid or a phenolic group in their formulae. These acids are capable of ionizing and hence releasing hydrogen ion in the solution. The acidic strength of these compounds is influenced by two factors, namely inductive effect and resonance. Let us discuss how these two factors influence the strength of the carboxylic acid. Inductive effect. The acidic character of carboxylic acid is due to the cleavage of OH bond in the C double bond OH group. As a result of the cleavage, the hydrogen ion is released as carboxylate ion plus proton. Substitution of electron withdrawing groups. Substitution of electron withdrawing groups increases the acidic strength of aliphatic acids. This can be easily explained in case of XHCH2COH, where X is an electron withdrawing group. Introduction of an electron withdrawing group X gives a positive charge to the carbon to which it is attached. This positive charge in turn influences the electronic distribution in adjoining C double bond O and COH bonds by withdrawing electrons due to positive charge. As a result, the OH bond becomes weak and ionization of the proton becomes easier than in the absence of this effect. Thus, the presence of fluorine in fluoroacetic acid makes it as a far stronger acid than acetic acid as shown below. Groups that increase the positive charge on the adjacent carbon atoms are called electron withdrawing and have plus I effect, while those increasing the negative charge density have minus I effect. Since the inductive effects increases with the increase in the number of substituents, it means that the strength of acid should increase with the number of electron withdrawing substituent. Thus, trifluoroacetic acid is more stronger than difluoroacetic acid, which in turn is more stronger than fluoroacetic acid. Then monofluoroacetic acid के बाद difluoro, then trifluoro. Thus the acidic strength of fluorine in substituted acids increases in the order. This electron releasing groups like methyl groups with plus I effect increases the electron density on the adjacent carbon as well as on the hydrogen of COH group. This discourages the cleavage of OH bond and lowers the strength of the carboxylic acid. Successive replacement by methyl groups in acetic acid progressively decreases the strength of substituted acids. As a result, trimethyl acetic acid is weaker than dimethyl acetic acid, which in turn is weaker than monomethylic acetic acid and acetic acid. pK values of some common carboxylic acids are given in table 7.4. To compare the relative acidities of corresponding acids, we have already learned that smaller the pK value, stronger is the acid. Trichloroacetic acid pK value of 0.65 is the strongest of all the listed values of acids in 7.4. Resonance effect plays an important role in determining the polarity of OH bond and hence influences the acid strength of carboxylic acid. The resonance effect differentiates clearly between the aliphatic and aromatic carboxylic acid. For example, benzoic acid is a stronger acid than its saturated analog, cyclohexane carboxylic acid. It is because the phenyl group is exerting an electron withdrawing effect, whereas the alkyl group is exerting electron donating, as is evident from the experimentally determined pK values. The effect of substituting alkyl group in the benzene ring has very little effect on the strength of benzoic acid. However, substitution of electron withdrawing groups in the benzene ring increases the acidity of benzoic acid by resonance effect. The resonance effect of nitro group is more dominant in the ortho and para position but not in the meta. Some of the pK values of these acids are given. Of the four benzoic acids given above, O-nitrobenzoic acid is the strongest acid. It is because the ortho group is nearest possible from the carboxylic acid group and exert both the inductive and resonance effect effectively. Strength of an acid or a base, effects of solvent on the acid's strength and leveling effect. Strength of an acid or a base depends largely on the nature of solvent used for its dissolution. Let us consider the dissolution of hydrogen chloride, chlorous acid in three different solutions: solvents, ammonia, water, and sulfuric acid. One can clearly see that HClO is the strongest strong base in ammonia, a weak base in water, and a strong base in sulfuric acid. Acidity and basicity of a protonic solvent plays an important role in choosing a solvent for a chemical reaction. The strongest acid which is available in a protonic solvent is that which results from the self-ionization of the solvent. Likewise, the strongest base available is that which results from the self-ionization of the solvent. Let us consider, for example, the following auto-ionization reactions. This H2 giving hydronium plus hydroxyl ion, ammonia giving ammonium plus amide ion. In aqueous solution, the strongest acid which can exist and which can be available for the reaction is the hydronium ion. It means all the strong acids known to be chemist appears to have exactly equal strength in aqueous solution. This results from the fact that acids such as perchloric, periodic, and hydrobromic and nitric and hydrochloric acid all are stronger proton donors than it is the hydronium ion. Thus, all these acids react completely with water to give hydronium ion. It means that the strong acids than hydronium are level to the strength of hydronium ion when placed in aqueous solution. In other words, water levels all the strong acids, namely HClO4, Hi, HBr, HNO3, HCl to the strength of hydronium ion as shown. Similarly, the very strong bases such as hydride ion, amide ion, and ethoxide ion all reacts completely in aqueous solution to yield hydroxide ion. X negative plus H2 giving HX plus OH negative. It means that all these strong bases are labeled to the strength of OH negative on reaction with water. In other words, solvent water levels all these strong acids, namely sodium hydride, NaNH2, and UC2H5 to the strength of all hydroxyl ions. For example, when sodium hydride, which contains the strong base hydride, is added to water, a vigorous reaction occurs when the brisk evolution of hydrogen gas and the resulting solution is found to be a solution of sodium hydroxide. Similar reactions occur when other bases like NaNH2 and sodium ethoxide are added to water. In order to compare the relative strength of strong acids and bases, the selection of the solvent is very important. The solvent selected should be such that it ionizes and strong acids and bases to different extents. Such a solvent which ionizes the acids and bases to different extents is called a differentiating solvent. Acetic acid can be used as a differentiating solvent because strong acids like HClO4, Hi, HBr, HNO3, and HCl will ionize to different extents in acetic acid. Acetic acid is a poor proton acceptor. Perchloric acid reacts completely, protonates completely as this, whereas other acids do not react completely because of incomplete protonation of acetic acid by these acids. On the basis of relative strength of different ionization of these acids in acetic acids, acids can be arranged in HClO4, Hi, HBr, HCl, H2SO4, and HNO3. Acetic acid is a leveling solvent towards bases such as cyanide, hydroxyl, ethoxide, and amide. This is because acetic acid reacts with the bases and levels them to the strength of acetate ion. However, strongly basic solvents such as liquid ammonia act as a differentiating solvents towards bases. Thus, it may be concluded that acidic solvents tends to differentiate between acids and levels of bases, whereas basic solvents tends to differentiate between bases and levels of acids. To summarize, all acids and bases stronger than the characteristic autoionized ions of the solvent will be leveled all off by the solvent, whereas acids or bases weaker than autoionized of the solvent will remain in equilibrium. Strength of oxoacids. The hydroxides of reactive metals are ionic compound and are strong bases. However, hydroxides of nonmetals are molecular compound and are acidic. The oxoacids can also be considered as the derivatives of water and can be represented by formula EOH, where E is the nonmetal which determines the acidity of the compound. The strength of oxoacid depends upon the combined effect resulting from size of atom E, electronegativity of atom E, and inductive effect of substituents present on E. Small and highly electronegative atom E will pull the shared pair of electrons between EO bond more toward itself. In turn, the oxygen will pull electrons from hydrogen bond in the hydrogen atom in the OH bond and makes the proton to dissociate easily. This makes the compound EOH to behave as an acid. Thus, higher the electronegativity of E, the more easily the proton is lost, and consequently stronger is the oxoacid. Acid character of oxoacids of halogens decreases in the given order as is evident from the pK value. Acidities of oxoacids are also related to the number of additional oxygen atoms, oxygens that are not a part of OH groups. attached to atom E. In these compounds, the acidity increases with increasing oxidation number of atom E. In the series of oxo acids of chlorine, the acidic strength increases in the following order. All these acids have only one protonated oxygen, only one OH group per. Chloric acid has 3, chloric acid has 2, and chlorus has 1 atom additional oxygen atom. These additional oxygen atoms tends to withdraw more electron density from hydrogen through the intervening chlorine atom. As a result, the polarity of OH bond increases more in case of acids containing larger number of oxygen atom. As a result, the tendency for the proton to dissociate increases in the order HClO4, then HClO3, then HClO2, then HClO. In general, oxo acids without extra oxygens are weak. Oxo acids with one extra oxygen atom are moderately strong, and oxo acids with two or more extra oxygens are strong acids. Alternatively, the increase in acidic strength is HClO4, then HClO3, then HClO2, then HClO can be explained on the basis of stability of conjugate base formed by the loss of H plus from the corresponding acid. Let us consider all the non-hydroxylic oxygen atoms attached to the chlorine by a double bond. Ionization of proton from OH forms an ion that is stabilized by charge distribution over the entire ion. The greater the number of pi or double bonded oxygen atom, the greater is the delocalization of charge, and consequently the stronger is the acid. Charge delocalization is minimum in ClO negative and maximum in ClO4 negative. It means that ClO negative will have minimum stability and maximum attraction for H plus ion. This means HOCl, the weakest acid. On the other hand, ClO4 negative will have the maximum stability and minimum attraction for H plus. This makes HClO4 the strongest acid. We have already learned that with the increase in the oxidation state of the central metal atom, the acidity of the acid strength increases. Thus, the order of increases in the acidic strength of oxyacids of chlorine is HClO, HClO2, HClO3, HClO4. The same argument of increased acidity with increase in the oxidation state can be extended to nitrogen acids, HNO, HNO2, HNO3, and in sulfur acids, H2SO3 and H2SO4. However, this generalization doesn't apply in case of oxoacids of phosphorus. The important known of oxoacids of phosphorus are H3PO2, PO3, PO4, in which the oxidation state of phosphorus is +1, +2, +3. Expected order of their increasing strength is H3PO2, PO3, PO4. However, exceptionally, all the oxoacids of phosphorus have been found to be weak acids with increasing acidic order in this order: H3PO2, then H3PO3, then H3PO4. This discrepancy in their acidic strength can be explained if we take into consideration the molecular structures of these acids as shown below, which contain pH and POO bond rather than the expected POH linkages only: hypophosphorus acid, phosphorus acid, and hypophosphoric acid. We know that dissociation of a proton in an acid is possible only by the hydrogen atom attached to the oxygen rather than the hydrogen directly connected to the central metal ion. The structure of hypophosphorus acid has only one OH acid. The second oxygen is unprotonated. As a result, H3PO2 is monobasic acid and gives only one hydrogen ion. On the other hand, H3PO2 and H3PO3 has 2 and 3 protonated oxygen atoms. We have already shown in case of oxochlorine compound that the acidic strength increases, the number of non-protonated oxygen atoms increases. However, there is only one non-protonated oxygen in all the three phosphorus compounds in this case. It means that the effect of non-protonated oxygen atom is more for one OH in H3PO2, less for two OH groups, and least for three OH groups. This explains the greater acidic nature of H3PO2 in comparison to H3PO3 and H3PO4. Empirical relationship for calculating pKa of an acid. Linus Pauling formulated an empirical relationship to determine the strength of various oxo acids that can be expressed as OMeOHN. The successive pKa value for oxo acids usually differ by 5 pKa unit. M is equal to 0, then pKa is very greater than 7, very weak acid. M1 pKa2, weak acid. M2 pKa minus 3, strong acid. M3 pKa minus 8, very strong acid. It is interesting to note that the number of OH groups appears to have little or no effect on the strength of the acid. Ricci's formulation. Another empirical formulation for the calculation of pKa of an acid has been developed by Ricci. pK is 8 minus M9 plus N4. M formal charge on heteroatom, N formal charge number of hydroxyl oxygen atoms. Formal charge is periodic group number minus half into number of shared electrons minus number of unshared electrons around the heteroatom. For HSO4 negative, M is equal to 6 minus half, that calculates is equal to 2, and N is equal to 3 according to Ricci. pK is 2. Experimentally, this value has been found to be 1.9. Similarly, the acidic strength of HClO and HClO4 can be calculated by using Ricci's generalization. You can see chlorous acid have M0 pK 8, HClO4 M3 pK 7 minus 7. The empirical values calculated according to Ricci's generalization are in good agreement with the experimentally determined pK values. It means that if one knows the formal charge on the central atom in oxo acid and number of non-hydroxyl oxygen atoms on the acid, the acidic strength can be calculated theoretically. Some of the pK values calculated by Ricci's formulation and the experimentally determined values are tabulated below. Similarly, the acidic strength of HClO, HClO2, HClO3 and HClO4 can be calculated accordingly. You can see this table. Then comes acidic strength of hydrated cations. Hydroxides of reactive metals are strong bases, whereas hydroxides of nonmetals are acidic. Hydroxides of elements near the borderline between metals and nonmetals in the periodic table are amphoteric. It means that they can react either as acids or bases. With acids, they react as bases. With bases, they react as acids. Aluminium hydroxide offer a beautiful example. In order to understand why aluminium hydroxide is amphoteric, we must consider the hydrated cation AlH2 whole 6 plus 3. When to a solution of AlH2 whole 6 plus 3, a strong base such as potassium hydroxide is added. Protons are transferred from the hydrated ion to the base. The following reactions that takes place are: addition of hydroxyl ion shifts all the four equilibria shown above to the right. As hydroxides are added to a solution containing AlH2 6 plus 3, insoluble AlH2 whole thrice OH3 written frequently as AlOH whole thrice is precipitated out, which dissolves in the presence of excess of hydroxyl ions. If a solution of strong acid is added to a solution containing aluminium AlH4 negative, H plus reacts with hydroxyl ions to form water. As OH negative is removed, all the four equilibria shift to the left. Insoluble AlH2 whole thrice OH whole thrice precipitates and then redissolves. Since AlH2 whole thrice OH whole thrice react with acids or base, it is amphoteric in nature. Similarly, hydroxides of chromium, lead, tin, and zinc are all amphoteric. It is important to note that when protons are transferred from hydrated cations and OH bond breaks, just as it does when protons are transferred from oxo acids. Equilibrium constant for the hydrolysis of hydrated cations can be measured. Equilibrium constant of some common metal cations are given in this table. You can refer to this table given here. A close inspection of the table 7.3 reveals that if charge and electronegativity are similar, then the smaller the radius of the ion, the more acidic the ion is. Okay, thus the order of acidity among the alkali metals is potassium, sodium, and lithium. It is obvious that the acidity of hydrated cations of alkali and alkaline earth metals decreases down the group of periodic table. If radii and electronegativity are similar, as in the case of sodium and calcium, then the higher the charge on the cation, the more acidic the hydrated ion. If one moves across the row of the periodic table from left to right, ionic radius decreases and charge increases. As a result, acidity of hydrated cations increases across a row. For example, sodium plus, magnesium plus 2, and aluminum plus 3. If charge and radius are similar, the greater the electronegativity of the metal, the more acidic the hydrated cation. Let us consider the case of magnesium plus 2 and zinc plus 2. In case of zinc, the electronegativity is more, hence the cationic zinc is more acidic than magnesium. The hydrated aluminium plus 3 ion with the highest charge, smaller radius, and relatively high electronegativity for a metal is by far the most acidic, listed in table 7 point as above. Role of solvent on the strength of Lewis acids and bases. A solvent plays an important role on the strength of Lewis acids and bases. A Lewis acid on hydrolysis may produce acid stronger than the Lewis acid itself. For example, boron trichloride, which is a Lewis acid, undergoes hydrolysis with the evolution of hydrogen chloride. Sequence of steps involved in the hydrolysis are outlined below. The first step involves the attack of water molecule with its lone pair of electron on the vacant 2p orbital of boron. Lone pair of electron from water is donated to the empty orbit of boron with the formation of a coordinate bond. Second step involves the loss of one HCl molecule. In doing so, one of the chlorine atom is replaced by one OH group. Third step involves the repetition of above steps till all the chlorine are replaced by hydroxyl groups and one gets boric acid. A Another interesting example when the role of a solvent is greatly appreciated is the hydrolysis of silicon tetrachloride to afford silicic acid. Distinguishing feature is the hydrolysis of boron trichloride and silicon tetrachloride is the presence of vacant 3D orbital in case of silicon. The mechanism of hydrolysis is the same excepting that the water molecule attacks the 3D orbital of silicon, forming an adduct involving a coordinate bond between silicon and oxygen. The adduct formed loses its cell molecules in steps till all the chlorine atoms are replaced by OH groups, yielding finally silicic acid as shown below. You can show. So this was all about our chapter. Thank you so much.